Imagine an invisible door in empty space, 31,000 kilometers above Earth. Pass through it, and an asteroid that should have missed us comes slamming back on its next lap around the sun. That door is called a keyhole, and it is the strangest, most precise concept in all of planetary defense. Today we step inside the lock. A miss is a miss, right? Not in celestial mechanics. A near miss is a gravitational handshake. And if that handshake happens in just the wrong spot, it can rewind the solar system's clock and put the asteroid right back onto a collision course with Earth. A keyhole is a patch of space, often just a few hundred kilometers wide. If the asteroid hits that patch, Earth's gravity does not just deflect it, it retunes the orbit so that the asteroid and Earth meet again, precisely, on a future date. Think of it as a lock. If the asteroid fits the keyhole, the impact date is sealed. Enter Apophis. Discovered in 2004, this 340-meter asteroid became the first object in history to make the Torino scale crackle. Early calculations showed a 2.7% chance of impact in 2029, but as astronomers gathered more data, they realized the real danger was not 2029. It was a keyhole. Here is the timeline. 2004, Apophis is discovered, and the odds of a 2029 impact briefly hit 2.7%. 2029, the flyby itself. Apophis will miss Earth by 31,000 kilometers inside the ring of communications satellites. But here is the catch. If it passes through a specific keyhole during that flyby, it will return in 2036 and hit. Apophis is about 340 meters across. Earth is 12,742 kilometers in diameter. Mass, Apophis is 50 billion kilograms. Earth is 6 trillion kilograms. But in 2004, the chance of this tiny rock hitting us was 2.7%, the highest ever recorded. Once the keyhole was ruled out, that number dropped to 0. A miss in 2029 by 31,000 kilometers was guaranteed, but the 2036 keyhole remained a threat until radar ranging in 2013 finally ruled that out too. How does a keyhole lock in an impact? It is a matter of timing. Earth orbits the Sun in 1 year. After the flyby, the asteroid's orbit is slightly changed. If its new period is exactly half a year, or 2/3 of a year, or any simple ratio, the two objects will be pulled back together like pendulums swinging in sync. That is a resonant return. The keyhole is the specific altitude that dials in that exact resonant period. Watch the dance. Apophis swings past Earth at 31,000 kilometers. The wedge marks the keyhole, a region just a few hundred meters wide. A fraction of a millimeter per second difference in velocity here is the difference between a miss and a resonant return. This is the most precise aiming problem in the solar system, and we have solved it. This is the counterintuitive beauty of planetary defense. The keyhole is the danger, but it is also the target. We don't need to miss Earth in 2036. We just need to miss the keyhole in 2029. And because the keyhole is so small, just a few hundred meters across, a deflection of a few centimeters per second, applied 5 years early, is guaranteed to work. Quick check before we close. An asteroid flies past Earth at 30,000 kilometers. What determines whether it hits a keyhole that sets up a hit on the next orbit? Pause the video and commit to an answer. Actually commit. The answer is B, precise altitude and timing at the flyby. The keyhole is a specific region in space that retunes the orbit into a resonance. Composition, magnetism, and spin have nothing to do with it. It is pure geometry and gravity. First, keyholes are real. They are tiny patches of space where a planet's gravity bends an incoming orbit onto a resonant return path. They are the mechanism by which a near miss today becomes a direct hit tomorrow. Second, Apophis taught us how to find and close keyholes. Its 2029 flyby is a guaranteed miss, and radar ranging has ruled out the 2036 and 2068 keyholes as well. The method works. Third, keyholes give us a target. A deflection of just a few centimeters per second is enough to slip past a keyhole and prevent a resonant return. Next lecture, We will see exactly how DART proved we can deliver that push. We will smash a spacecraft into an asteroid and watch it move.